Alright, so in this video we'll go over a few properties of isolated conductors which will be useful throughout the course. So first of all, what is an isolated conductor? An isolated conductor is basically just any conductor that's not connected to any other conductor. So for example, if you have this metal block that's sitting on a wooden tabletop surrounded by air, that would be an example of an isolated conductor. So a conductor that's completely surrounded by insulators and not connected to any other conductor. Okay, metal block. So this is an example of an isolated conductor. All right, now property number one. So in a conductor, we know that there are free electrons, right? So in an isolated conductor, we say that all charges are at rest. And I'll just qualify this statement at rest a little bit. So what that means is that the free electrons are not, there is no large scale motion of the free electrons. They're not moving in any particular direction. The nuclei of the atoms are not moving at all, because in a conductor, we know that in a solid, the atoms more or less maintain their positions. So these squares with pluses that I'm drawing are the atoms. You can think of the plus as the positively charged nucleus. And so these atoms are vibrating in place, but they are not really changing positions. And what about the free electrons? The free electrons might also be vibrating, and they'll have a random zigzag thermal motion. But in general, the free electrons will just stay where they are. On an average, their position is not going to change because they really have no particular reason to move one way or the other. So apart from their random thermal motions, the atoms and also the free electrons more or less stay where they are. So that's what I mean by at rest. And so I should say aside from their random thermal motion. Now, since we're mostly going to be talking about metallic conductors, we will not bother with the motion of the positively charged atoms at all, because they will always remain in place. So we are only going to be concerned with the motion of the electrons. And so when you have an isolated conductor, the electrons are more or less at their positions at a fixed location. They might be vibrating around that location, but they'll more or less be at a fixed location. So all charges are at rest inside an isolated conductor. Okay, the second property is that any excess charge that you put on the isolated conductor always resides on the surface of the conductor. So let's say that you have this block of metal and you put some charge on it. So we've seen in class how you can put charge on an object. You can just, if you want to put negative charge on it, you can just rub rubber rod against fur, and then the rubber rod will have excess electrons. It will get negative charge, and then you uh, rub that rubber rod against this metallic block, and you'll transfer some excess electrons to this metallic block. So now there will be some excess electrons in this block. Just draw the block again. These are the atoms of the block, and there are also free electrons. So these blue dots are the free electrons, and what you just did was you transferred some excess electrons to this block, just to distinguish between the electrons that were already there and the new excess electrons that you transferred. I'm just going to draw the excess electrons with a different color, maybe yellow. So what I'm saying now is that these excess electrons that you gave to this block in the process of charging it will always reside on the surface. So these are the excess electrons. Excess, it's excess electrons in this case. Oops. But you could transfer positive charge as well. And these are the pre-existing electrons that were already there. Okay, so the point is that the excess charge will always reside on the surface of the conductor. Now, why will the excess charge always reside on the surface of the conductor? The reason for that is that um, suppose there was some excess charge in the interior of the conductor, right? Remember that electrons have complete freedom to move around inside a conductor. So suppose there were some of these excess charges inside the conductor, they would just repel each other away. And so they would just get as far, they would want to get as far away from each other as possible. And as a result of that, they would all end up on the surface of the conductor. So it's mainly their mutual repulsion that causes all these excess charges to end up on the surface of the conductor. All right. The third property, it's very, and this is very important and it's a bit subtle, it's that the electric field in the interior of a conductor, I should say isolated conductor is always zero. So in the interior of an isolated conductor, there is no electric field. Why is that? Now, if you just have an isolated conductor, just sitting by itself, not charged or anything, then there is no electric field in the interior of the conductor. Um, However, suppose you bring a charged object. Let's say that you bring this charged object over here, and that produces an electric field. And I'll draw the electric field, um, draw some arrows to indicate the electric field. So this produces an electric field. All right. Now, this electric field is passing through the conductor, right? Okay. The moment you produce this electric field and there's an electric field in the interior of the conductor, what's going to happen is this electric field is going to act on the free electrons in the conductor. So initially the free electrons were all randomly distributed throughout the conductor. They more or less filled up the entire volume of the conductor and uniformly distributed in the conductor. But once you have this electric field, what happens is the electric field will start acting on the free electrons. And what does an electric field do to a negative charge? It pulls the negative charge in the direction opposite to itself. And so as a result of that, the electrons, and I'll draw the electrons this time as circles with little minuses, so it's clear that they are electrons. So the electrons will all be pulled opposite the direction of the electric field, and they will all start aggregating. The free electrons will all start aggregating on the left side of the conductor. Now, you know that negative charges produce electric fields which point towards them. So if you have a large number of negative charges aggregated over here, and remember that since the negative charges have moved to the left, there are bare positive charges on the right. So previously the negative charges and the positive charges were uniformly distributed throughout the material, but now the positive charges are still uniformly distributed, but the negative charges have accumulated on the left of the conductor because of this electric field. And so what happens is that you've got this line of positive charges on the right and line of negative charges on the left. And so what's going to happen as a result of that is that these internal charges will also have an electric field. And the electric field due to these charges that have been produced in the interior will look like this. It'll point from the positive to the negative charges. And as a result of that, the external and external and internal electric fields will eventually cancel out. Remember that since the free electrons have infinite freedom to move around inside this conductor, they will keep accumulating on the left of the conductor, and as a result of that, there'll be more charges on the left, more negative charges on the left, consequently more positive charges on the right. And the result of that is that the electric field will keep getting stronger and stronger. The internal electric field will keep getting stronger and stronger until it completely cancels out the external electric field. So this is the internal electric field. And the blue one, of course, is the external electric field. So the internal electric field will keep getting stronger and stronger until it cancels out the external electric field. And then you will have zero electric field in the interior of the conductor. And so basically the point is that whenever an isolated conductor is subjected to an electric field, the charges in the conductor will rearrange themselves in order to cancel out electric fields in the interior of the conductor. Now, you might say that this is looking familiar, this rearrangement of charges in a conductor when you bring an external charge near the conductor. We saw that in the very beginning of this course. And indeed, it's exactly the same thing. This, what you just saw, is just the phenomenon of electrostatic induction.